Determine the nature of the critical point of the system dx over dt equals to x plus y, dy over dt equals to 3x minus y. Also find the general solution of the differential equation governing the path. Solution: the given system is dx over dt equals to x plus y, dy over dt equals to 3x minus y, equation 1, which is of the form of dx over dt equals to ax plus by, dy over dt equals to cx plus dy. Here a equals to 1, b equals to 1, c equals to 3 and d equals to minus 1. Now ad minus bc equals to 1 into minus 1 minus 1 into 3 equals to minus 1 minus 3 not equals to 0. The characteristics equation lambda square minus a plus d into lambda plus ad minus bc equals to 0 becomes lambda square minus a is 1, d is minus 1 into lambda plus a equals to 1, d equals to minus 1 minus b equals to 1 and c equals to 3 equals to 0, which implies lambda square minus 0 minus 4 equals to 0, which implies lambda square equals to 4, which implies lambda equals to plus minus 2. Now since the roots are real and unequal and of the opposite sign, therefore the critical point 0, 0 is a saddle point. Here the critical point 0, 0 is unstable. To find the path, eliminating dt from 1, we have dy over dx equals to 3x minus y upon x plus y, equation 2, which gives the slope of the pairs in the xy plane defined by the solution of 1. Now from 2 can be written as x plus y dy equals to 3x minus y dx. Now integral of 3x minus y dx equals to 3x square upon 2 minus xy plus constant. The coefficient of di free from x in y whose integral equals to y square upon 2. Hence the solution is 3x square upon 2 minus xy minus y square upon 2 equals to c, which implies 3x square minus 2xy minus y square equals to c, equation 3, where c is an arbitrary constant. So equation 3 is the equation of the family of the path in the xy phase plane.